Okay, so my project is called the FMQSM platform for next generation silicon photonic integration. So if I can explain the acronyms and the term silicon photonic integration to you guys, I would be happy. Okay, so let me start with trying to explain silicon photonic integration. So actually, Sasan is an expert in this area, so I'm just going to say a few words. In silicon photonics, we try to build circuits for light on silicon substrates using, CMOS compatible processes that use, IC chips. So the applications of silicon photonics includes optical communication, sensing, especially for bio applications, LiDAR, quantum information, neural networks, and computing. So the picture on the left is actually a circuit for quantum interference. So you see the delay lines, splitters, and interferometers, etc. But by far the biggest application of silicon photonics is optical communication. So for example, you can use silicon photonics to make a coherent optical modulator. You can see the light coming from the left, and the top part modulates the real part of the light, and then the bottom part modulates the amplitude of the bottom path, but adds a power to phase shift. So it essentially modulates the imaginary part of the E field of light. That way you can create quantum signals like this. Electronic people have done this for decades. Optics people are just following in the recent decade. And similarly, in the coherent optical receiver, you need to detect the electric field of light. In order for you to do so, you have to do this interferometrically. So the light and a local oscillator comes in from the left, and the top interferometer detects a real part, and the bottom part has a 90-degree phase shift in the local oscillator, and it detects the imaginary part. And this device here in the box is called the optical 90-degree hybrid, which is the counterpart of the electrical 90-degree hybrid. So here is a picture of a commercial coherent transceiver. The pioneers of silicon photonics technology industry made themselves a lot of money. Acacia, this company here, Acacia, was sold to Cisco last year for about $4 billion. And this is a coherent transceiver. It mirrors what I said in the previous two slides. So this is the transmitter, and this is a receiver, and this is where local oscillator is. Those are the the modulators and the splitters and stuff like that that I mentioned before. And the chip is very tiny inside this package, and this is in reference to a quarter. Okay. So we also in optics we also do polarization multiplexing. So that's sort of beyond the discussion here today. So actually, Acacia didn't have their own clean room. So as we said, this is a CMOS compatible process. So Acacia used global foundries, and there are lots of foundries that are offering services for you to do silicon photonics. TSMC, we heard a lot of story about them nowadays. Samsung, small players like Tower Jazz, AIM Photonics, that are advanced micro foundries. And of course, IMEC also offers a certain level of foundry service. So if you look at the platform, the gray here is the silicon substrate, and then there is an oxide layer, which is yellow, and then on top of that, there is a 2.2 kiloangstrom or 220 nanometer silicon, where you can make waveguides. This is a modulator, PN junction silicon modulator. And then there's a detector, germanium, silicon germanium detector. This is for 1.55 micron applications where germanium absorbs, and other devices like that. of course, there's electrodes and for these active materials, active devices. There's 2 layers metal, and you see there's a heater here also, and I'm going to explain why there's a heater in the next slide. But on top of the silicon layer, there is a silicon nitride layer, which can also guide light. And IMEC has a lot of PDKs, processing development kits for silicon, but they don't have anything on silicon nitrides yet. And that's part of what our collaboration is about as well. So, so the motivation for our project with IMEC is as follows. So the silicon photonics industry is advancing, to higher speeds and large scale integration. And the wafer size is, 8 inches or 12 inches. But the wafer scale yield and performance variability across the wafer is problematic at this point. And the underlying reasons are that, very small changes in the dimensions of the waveguide affects the performance of the silicon photonic devices. So the example that I, often give is, let's say a Mach-Zehnder-based wavelength filter. So it's, kind of like an FR filter in electronics. It has a 1 nanometer per nanometer sensitivity to waveguide width in terms of the center wavelength of the filter. And it shifts 2 nanometers per nanometer of the height of the waveguide. And it shifts as a function of temperature as well. So it's very sensitive. Nanometers can bring your signal completely out of this, the filter. Our optical channel spacing is on the order of 0.8 nanometer. So, but current fabrication technologies produce about 10 to 20 nanometers variation in waveguide width across the 8-inch wafer. So that's where the thermal the heater comes in. The thermal optic tuning is needed so that you can tune the characteristic devices to the operating wavelengths that you need. So that obviously brings complexity, power consumption, cost, etc. So we are trying to address this wafer scale variation yield problem for this seed project. And our solution is to use a field mode or quasi-single mode waveguide platform to address this issue. And at the same time, we can see that we can improve the performance in some other areas as well. So right now, almost all the silicon photonic devices uses single mode waveguide. It only supports a fundamental mode. And what we are saying, we're going to widen the waveguide a little bit so that it supports a field modes. And if you compare the fundamental mode between the field mode and the single mode, you can see that the tail of the single mode, extend out of the core region a little bit more than this. Okay, so we are trying to incorporate, instead of just single mode devices, we are trying to make field mode devices, and then that's the first part of the project. The second part is try to use this platform to demonstrate a transceiver for free space optical communication, which is capable of electronically compensating the wavefront distortion. Okay, so let me go a little bit into the detail of these points. So I kind of already said the underlying physics, why we think it's going to solve the wafer scale yield issue. So essentially, when you go from the single mode fiber to the single mode waveguide to the field mode waveguide, then the property of the fundamental mode, which now is well confined inside the waveguide, is now going to be affected by the geometry of the field mode waveguide as much as the current single mode waveguide. And the reason we call this quasi-single mode is because even though the waveguide supports a few modes, our signal interest will only be in the fundamental mode. So we don't use the other mode. The other modes are auxiliary. It just helps us to solve the yield issue and provide some other benefits that I'm going to discuss here, including reduced loss, enable high speed, and also improve nonlinear performance. And I'm going to show you some preliminary simulation results where we plotted the effect index, basically the phase velocity of the light, and the loss and the mode area as we change the waveguide width. So let's look at the first one, which is effect index. As you can see, now beyond about 2.53 microns of width, the speed of light doesn't change anymore. So, all these, filter center frequency shifts is not going to happen anymore. On top of that, if you look at, this should be B, okay, the loss as a function of width, basically, most of the losses, at least in silicon nitride waveguide, comes from the roughness of the sidewalls. And because the fundamental mode is hiding inside the core, so as you make the waveguide wider and wider, it hides better and better. It just doesn't see the roughness anymore. So you can reduce the loss quite a bit. And then as you increase the width, the mode area also increases. This is important for when you have to handle a lot of power. As we increase size of the circuit, you will need a lot of optical power to drive it. And the nonlinear effects, normally we don't want nonlinear effects, and nonlinear effects is proportional to the intensity of light, which is power divided by area. So if you reduce the area, then you can increase the area, you can reduce the nonlinear effects, make it more tolerant. So then the second part of the project is to build this integrated free space optical communication receiver with the capability of doing wavefront correction using electronics. So, optics people actually have spent a lot of time trying to do this using pure optical technologies, but with the advances of DSPs and this integration, we probably can do this electronically. So in free space communication, we have to send light through turbulent atmosphere. It's essentially a multipath interference channel. The time constant is on the order of a millisecond, and depending on the condition, the turbulence, there can be sort of like 100 independent, paths for the signal to go through. So our proposal is to do coherent detection for each of these paths, and then do a digital phase estimation. These are all the terminologies I think that all the engineers, electrical engineers are very familiar with. And then we do maximum ratio combining after subtracting these phase errors. So that's how we do electronic wavefront correction. All this coherent detection, signal measurement that feeds the DSP has to be done using optics. And this is sort of a rendition of the circuit that we are trying to build. All the active elements are in silicon, the yellows, the red, silicon, and then all the passive functionalities are on silicon nitride, which is the blue. Okay, so you see the silicon to silicon nitride transition where we tap a little bit of light to, for example, measure the power of each channel, and then do some low speed, phase estimation, and then this is a high speed, actually signal detection, etc. And our follow-up plan is obviously my interest in joint externally funded research, especially in free space optical communication, from DoD organizations such as RFIL or the Space Development Agency. IMAC is interested in, beyond communication. They're interested in quantum, AI. And then we have been actually providing sort of a testing, transceiver testing services to IMAC. IMAC has internally trying to develop their coherent transceivers, and we have the equipment to do these testing, the very high speed arbitrary waveform generators and real-time scopes, above 30G. We have those equipment in our lab, and this is sort of our bread and butter. And this is how we got in contact with IMAC and to start with. So in that sense, I am an accidental silicon photonics engineer because most of the work that I do is on the system level. And this is our group. We have students working on optical amplifiers, optics for AI, secure communication, key distribution using classical methods, label-free imaging, directed energy, and mode multiplexing, which is pure communication. They all do some sort of communication projects as well. And our current sponsors include ARO, ARL, ONR, NSF, DARPA, Fujitsu, Omega Photonics, of course now IMEC. And I collaborate with 5, 6 faculty members at CREO, so they have co-PIs with me on these funding. So with that, I hope that I will have a chance to collaborate with people in the College of Engineering, Murat, and we have been talking about trying to collaborate on free space communication for a while, and we tried and we haven't succeeded so far. Hopefully we'll be successful sometime soon.
Okay.
Thank you.